All right, so we take this idea of differential equations, we take this idea of separating differentials, and we bring it into some real-world problems involving growth and decay. Unfortunately, most of these are not very happy things. They're like radiation, spread of disease, zombie invasion, that kind of stuff. So unless that makes you happy, then it would be a good thing. Okay. So, separable differential equations and the laws of growth and decay. Just sounds impressive. Bring that up at the kitchen table tonight. Guess what we did today? Separable differential equations and the laws of growth and decay. And they'll either be impressed or just laugh at you. Probably the latter. Do you remember the Pert equation from pre-calc? No? Do you really not?
No.
How many people don't think they did the Pert equation in pre-calc? Holy guacamole. That's not good for me, but it'll be good for you because I can teach it the right way, because who knows who has the pre-calc, especially you had Knupke. Who had Knupke? What a train wreck, right?
Yeah.
She can't get out of her own way half the time. For those of you that did do the Pert equation in pre-calculus, I'm guessing this magic equation appeared out of nowhere. Go forth and use the Pert equation. Thou shalt solve thy problems. In calculus, however, we're going to derive where that equation comes from. This will be fun. And then, always, believe in yourself, because I believe in you. And you. You, not so much. Okay, here we go. Pert equation. Now, if the Pert equation is not given in that true form, the Pert equation is actually in that form. Okay. You might have also seen the first P as an A for the amount. Traditionally, however, it's given this way. P equals P naught, that's how that's said, P naught, E raised to the ERT. P is the final amount. Anybody know what P naught stands for? Initial amount. Good. Starting amount. Anybody know what E stands for? Who can do it? Can you fire off all the digits of E? Oh, that's a good start. I spent like 20 minutes on this with a $20 bill.
1828. Yeah.
What president was he?
7.
2.7, 1828, 1828.
The rest. Oh, $20.
45, 90, 45. Very good. Folded it into a triangle when we were done. R is, aside from being a pirate's second favorite or letter, you know what its favorite letter is, right? The C. Good. Yeah. It's a growth or decay rate. If it is a growth, that number R will be positive. If the quantity is getting larger, if more zombies are appearing, if there's more bacteria, if more people have COVID, that's a growth. Decay, the number would be negative. Radiation decays. What's T? Time, correct. So in pre-calc, if you did cover this, what would have happened is you would, oh, by the way, how many variables in that equation? Sorry, let me rephrase my question. How many variables on the right-hand side of that equation? 3, correct. In order to solve that, you need to know 2 of the 3. Technically speaking, however, there are 4 variables in that equation because the final amount comes into play. So now you've got 4 variables, you need to know 3 of the 4 in order to solve it. If you know 3, you then need to know how to solve for the one that you're missing. Okay, so in other words, if you don't know capital P, you just plug and chug into your calculator. It's not rocket science. If you don't know P naught, that's also not difficult to solve for. Not knowing R or T will require a little bit more work on our part, which we'll go over as we go through these problems. Okay? So, again, pre-calc, you're given this magical equation, you plug and chug and you solve. Okay. In calculus, we're going to take a different approach. Now, that first equation on the left, down below, is the same equation, just rephrased. Since we've gotten used to C as a constant, we'll put in C instead of P naught. And then instead of R for rate, we'll put in K, because again, that's common. You'll see why K pops up. What we're really going to focus on is this right-hand part. dy dt, also known as a rate. Because you'll recall when we did derivatives, derivatives represented three things. The slope of the tangent line to the curve, instantaneous velocity, and a rate of change. And for us, the rate of change is going to tie into time because we're doing real-world problems. You'll see that cy, sometimes it'll be ky, where k is used as a what's called a proportionality constant. This will make a little bit more sense when we get into the examples. Okay, so for those of you that saw the Pert equation last year, this should seem fairly familiar. For those of you that haven't, this is a whole new world. Feel free to sing the song.
It's a whole new world.
Beautiful. And we have that recorded. Thank you. All right, here we go. Let's talk about some bacteria.
Sorry. I didn't know it would make it.
Sorry, we've got that recorded down here. Molly's going to go home and listen to herself drop that can in the garbage can over and over again. We turned it like a remix.
I should.
You can all read, but I'll read it just for prosperity's sake. The number of bacteria in a culture increases from 600 to 1,800 in 2 hours. Assuming the rate of increase is directly proportional to the number of bacteria present, find blah, 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 A and B. Okay. In a pre-calc class, we would start with the Pert equation. You plug in your initial amount. What's the initial amount, by the way? 600. What's your ending amount? 1,800. What's T? 2. What's R? Unknown. That's what we'd solve for, and you go from there. Okay. This is calculus, however. We're going to take a different approach. So the different approach we're going to take comes from this little guy. Okay. I'm going to choose little b to represent the number of bacteria. Bacteria. Right. And I'm going to use k as the proportionality constant. So, assuming the rate of increase, it's a rate, so it's going to be a derivative. dB dt. The rate of increase of the bacteria, dB, with respect to time, dt, is equal to, not equal to, sorry, is directly proportional to the number of bacteria, kb. Does that make sense? Okay, and I'll put a note in here. Up here, proportionality constant. There, okay. Okay, so far. Now we do calculus. Pre-calculus, you're not going to do calculus. Calculus, we're going to do calculus. Eric, what's rule number 1?
Separate the difference.
Oh, I'm so glad you're here, buddy. Eric, would you like to leave the K over here, or would you like to bring the K over to the other side with the B?
Let's leave it where it is.
Great answer. Okay, multiply both sides by dt, divided both sides by b. Life is grand. Take the integral. Okay, now, this is where we have to talk a little bit about the differentials, because most of the time when we're working with differentials, that differential is either a dx or a dy. This one's a dt. Okay, so let's do the left-hand side first, because it's easier. What's the antiderivative of 1 over b? Okay, now technically speaking, it would be the natural log of the absolute value of b, but can b be negative? No, we can't have negative bacteria, so we'll get fancies in our panties and drop the absolute value there. What is the antiderivative of k dt? Good. You might be saying to yourself, oh, it's 1/2 k squared. No, our variable is t. So therefore, Matthew said this would be KT. It's Katie. Wait. I don't know why I'm cracking up. I'm so tired. Let's solve for B. I have an excuse why I'm tired. I'll tell you a sad story in a little bit. I just don't want to record it. We do the E2 trick. By the way, thank you, Eric, for playing into my my plans. We do the E2 trick. Bring that up here, and we get B is equal to e to the KT plus C. Based on what we just talked about when we were doing the other problems, this can be rewritten as e to the C times e to the KT. And as we addressed earlier, what's e to the C? C. So B is equal to C times e to the KT. Well, that equation should look fairly common or familiar. That's the Pert equation, just rephrased. All right, questions on that process. So we just used some calculus to get where you would have been with pre-calculus. We haven't even solved the questions yet. So now let's do that. Can I erase this because I need some working room? We're good? All right. Okay, so we talked about this already. Let's dive into this. I know that the initial amount is 600. I know the ending amount is 1800. I got an E. I don't know what K is, and I know that that takes 2 hours. Why am I doing this? Because I don't know what the growth rate is. By the way, should my answer be positive or negative? Positive. Bust out your calculators, by the way. Now, important step. You might want to do the natural log trick, which we're going to do in a second. But before you do the natural log trick, you have to be sure to isolate the exponential term first. In other words, divide both sides by 600. Whoops. K2. Take the natural log of both sides. So that is the natural log of 3 is equal to 2k. So k is equal to the natural log of 3 divided by 2. Little help here is approximately 3 decimal places.
0.549.
You must store that number. Don't use a decimal approximation. It will screw up the answers. Okay? Now, to answer part A, what is the formula? Well, the formula would be B is equal to 600 e to the 0.549t. There's my general equation. Okay, so by doing a little bit of work, we are able to eliminate C, and now we have it down to 2 variables. So there's only 2 questions you can ask. After this much time, how many bacteria do I have? I have this many bacteria. How much time did it take? So I'll let you do part B. Go ahead. Plug and chug. As our German friends would say, plug und chug. Plug 4 in for T. Make sure you use parentheses. You got an answer, Adrian?
5,400.
Do they agree?
Yeah.
Okay. It's a word problem. 5,400 what? stuff on the board now in blue is all pre-calc stuff. The stuff that we did previously in red is the calculus component to growth and decay. As much as I would like to say to you on these assignments, oh, just go use the Pert equation, that's not what's going to happen on the AP test. They're going to expect you to be able to derive this monstrosity. So we're going to continue practicing that. It will seem fairly repetitive, but then every once in a while there's a little twist thrown in that makes things interesting. Sure. Are we good? Can I move on? All right, beautiful. Let's talk about radium. Do you all know how radioactivity works?
Yes.
Do you know what a half-life is, other than a phenomenal classic video game? Probably one of the greatest video games ever made. No? Yes? You know what half-life? Does anybody not know what half-life is? Don't be bashful, because this is important. We're all good? Delaney, you know? Okay. Half-life is the amount of time. Okay, let me back up. Radioactive material decays over time. It just kind of magically disappears. Half-life is the amount of time it takes for half of the quantity to disappear. So if I've got 10 pounds of radium sitting here, aside from us all being dead, it will take 1,600 years, and after 1,600 years I'll have 5 pounds. After another 1,600 years I'll have 2.5 pounds. After another 16, so you see, it never really goes away. Which is why Chernobyl, you all know what Chernobyl is, right?
Yeah.
Nuclear meltdown. That's why it's still not habitable, because even since the 80s, I think it was, there's still large quantities of radioactivity because it takes so long for this stuff to disappear. There are other things that have very quick half-lives. Okay? I can't think of one in particular, but there are things that disappear very quickly. If you've heard the term carbon dating is a process by which you measure the age of a material by looking at how much carbon is left in it and working these kinds of problems backwards. It's probably a lot more involved than that, but I'm a math teacher, we're just going to go with it. Okay? So we're good so far. The reason I chose this is because something strange happens. It appears that I didn't give you enough information. Okay? Radium decays exponentially and has a half-life of 1,600 years. Well, how do I go on from there? We can do it from scratch, but we're going to cheat on this one, and I'm just going to start with the Pert equation. Okay? Because there's something I want to work out with this that's different than what we did in the last one. So I'm just going to go to Pert equation. A equals P naught E to the KT. What do we know in that equation?
Half-life.
We know it's half-life, which is A, P naught, E, K, or T. No,
Wait.
it's T. It's time. Okay. So it would seem like I don't have enough information. But I do. How do I know? Well, I know that if I start with some quantity, and you can decide how you want to approach this. You can make up a quantity. Forget about problems A and B, by the way. I'm just dealing with the first line. You could just make up a quantity and say, oh, I have 100 pounds of radium laying around. After 1,600 years, how much radium will I have? Right. What did I say, 100 pounds? Right, I've had 50 pounds. If I start with P naught radium, how much will I have after 1,600 years? Half P naught. And one thing I said is the first thing to do is solve for that. So regardless of what these two things are, I'm going to end up, with that. And that's a really important idea, and I want to make sure you get that before we move on. Yes? Doesn't matter how much you start with, after 1,600 years, I only have half of it left. Now, there's a contrary idea to this. It's something called a doubling time, or a doubling life. That has applications in like investments. So Conrad graduates from high school, his family gives him $10,000. He'd like to know, hey, Jim Bob at Chase Bank, how long will it take me to double my money? Right, so you need to know your interest rate, you need to know Well, that's it. You need to know your interest rate, right? Because then you could calculate how long it's going to take to go from $10,000 to $20,000. That's a doubling time. We could also say Conrad doesn't know how much he's going to get for graduation, but he still wants to know when he takes that money and invests it, how long will it take to double his money? As long as we know the interest rate, we can do that calculation. Okay, does that make sense? Doubling time versus half-life. They're the same thing, just one's going to be 2, the other one's going to be 1/2. So I assume you see that we can solve for k, yes? Okay, go ahead, solve for k. I'm going to talk while you're calculating. Will my answer be positive or negative? It'll be negative because it's a decay problem. Very good. Don't be bashful. In other words, somebody tell me the answer. Go, Connor.
Negative 4.33 times 10 to the negative 4.
Confirm? Can you give that to me in decimal form?
Move it over 4 times.
Thanks, Einstein. 0.0004. What did you say? 43? 433.
There's a bunch, bro.
Yeah, we'll just stop there. Now, that's more than 3 decimal places, but obviously if I go 3 decimal places, I'll have 0.000, and that's redonkulous. Which again, I assume you stored. Beautiful. Okay. This value that we just calculated applies to all radium. Every element that decays has a decay constant that is associated with it. I'm sure you learned this in chemistry, right? No? What is going on with this place? Unbelievable. All right, let's answer some questions. Find the amount. Find a formula for the amount of Y remaining after 50 milligrams of pure radium after T years. Okay, well, that's easy. A is equal to 50 times E to the negative 0.123433T. Good. And again, in calculus, if we were doing this, we would do something like dy dt is equal to ky. And go and solve that. But I didn't want to do this. I just wanted to get right into the Pert equation to talk about half-life. Okay. Part B, when will the amount remaining be 20 milligrams? How long does it take for 50 milligrams at this decay rate to end up as 20 milligrams? Go ahead and solve that, please. By the way, will it be more or less than 1600? More or less than 1600? More, right. 25 would be at 1600. Any more disappearing would be greater than 1600. Remember, isolate the exponential first, divide both sides by 50. Take the natural log of both sides, plug and chug. Sounds good to me. And so, you got something close to that? You got 2160. Did you store your number? What did you all get? 2,115 or 2,116? 15? Uh-oh. 2,115 point?
0.85.
3 decimal places.
0.85.
0.85. I didn't hear the 8. I'm sorry. What are my units there, Em? Years. That's a long time. I don't know why my S is dotted like that, but I'll leave it because it looks kind of fancy. Okay. How are we doing so far? Growth problem. Decay problem. I believe next we have Newton's law of cooling. Is that accurate?
Yeah.
Beautiful. You all know Newton, right? You'll also recall we had a little history about Newton, about how big of a jerk he was. Irrelevant to the problem, we'll just go with it. Anybody know Newton's law of cooling from chemistry? Good, I would be worried about you if you did, because that would be nerdalicious. Newton's law of cooling, at the rate at which an object cools is directly proportional to the temperature, proportional to the difference in temp between the object and the surrounding medium. In other words, the room temp. Okay? So we're going to put a little slash here and say we got to put all this gunk together into an equation before I start answering questions about the problem. Okay. The rate at which the object cools. So let's make, we can't use T for temperature because we already have T for time. Let's do Z. Temp of object. Okay. So the rate at which an object cools, dz dt, is equal to the difference in temp between the object and the surrounding medium. Oh, here it is. That's what I needed. I think we're good, right? Because we know the room temp is 75. The room temp doesn't change at all, does it? Oh, sorry. I forgot a constant. Because it's proportional. Let's use C instead of K for a change. Okay, so the room temp, I guess I needed to read further ahead to see what the temperature in the room is. This is kind of a big deal. As soon as you introduce a non-defined variable in the equation, you need to define it, especially on the AP test. They're going to want to know, well, what the heck is Z? You know, the assumption is T is time. The assumption is C is a constant. If you use C or K, it doesn't matter. Go from there. Eric also helped out when he suggested that other problem, because this is similar to the one that we did with the y plus 3, right? So this would be 1 divided by z minus 75, dz, whoops, that's a z, is equal to c dt. And again, I would leave the constant on the right-hand side. Integral of both sides. Ct, and then what's this? Well, u is equal to z minus 75, so du is equal to 1 dz. So it's actually going to end up being the natural log of the absolute value of z minus 75. Okay, so far? Do the E2 trick. Z minus 75 is equal to e to the ct. I made a mistake. Where is it? No, it goes away because we're dealing with a value there. Matthew?
You didn't separate e to the c and e to the t.
Say again?
You didn't separate e to the c and e to the t.
I did. Where are you talking about?
Last year. There.
Oh, I'm not done yet. No, I still have a little bit more work to do, but I made a mistake before that. It might be a little hard to recognize. Are you raising your hand, Mason?
Yes, couldn't it be plus or minus e to the CT?
Not there yet. I think this might be a little confusing. Let's change this to a K. And it might be a little bit easier to see where my mistake is. M. I need a plus C, correct. This is a plus C. So then this would be K plus C. We do the whole spiel again. C e to the kt for reasons we already discussed. So z is equal to C e to the kt plus 75. That's my final equation. 3 variables. Z, K, and T. So if I come to this second equation here, or this second sentence I should say, an object cools from 125 to 100 degrees in half an hour. Surrounded by an air temp of 75. So what's C? What's my starting amount? 125. What's my ending amount? What's Z? 100. Solve for K, because you need the growth rate or the decay rate. Will it be a growth or a decay? Is the number getting bigger or smaller? Smaller, therefore decay, right. Solve for that, then you can go ahead and figure out the answer in the second part, which is find the temp at the end of the half hour. Warning, the AP test loves to do this. They'll play with time. So notice half hour. You have to decide early on what units are you working in. Are you going to work in minutes? Are you going to work in hours? Usually, it's easier to work in hours, but you can do either one. If I choose to put 30 in for T, that's okay, as long as you realize that everything then has to be in minutes. What becomes a common mistake is the problem will say something like, it takes 2 hours for the temperature to change from 125 to 100, and what's the temperature after a half hour? So then all of a sudden you put 30 in for the half hour and it screws everything up. So make sure you stay in the same time unit throughout the whole problem. Okay, questions? Beautiful. Couple things to remember when you're done. Make sure you include units, because it is a word problem. Number 2, ask yourself a simple question. Does that answer make sense? Okay? For those of you that have had chemistry or are in chemistry, can the temperature of the coffee ever get below 75 degrees? No, that's absurd. What we're ignoring, for the chemistry nerds in the group, maybe a little bit of physics, what's happening to the room when you put the cup of coffee in there?
It's heating up.
It's heating up. We're just going to pretend that doesn't happen. We'll assume that that's a negligible quantity. Okay? But yeah, from a pure chemistry standpoint, any fluctuation from the norm causes a variation in both sides. Wow, that sounds really impressive, didn't it? Yeah, I use a lot of big words, and there's a lot of multisyllabic words. Multisyllabic, multiple syllables. Right. Like disestablishmentarianism. Okay, we good? I think we're done, right? Is there any more after that? I think we've had enough. Yeah, day 61.
Oh, wait. It's like mine did.